Welcome students. Today we would see the proof of Laurent's theorem of complex analysis. What Laurent's theorem states that if function fz is analytic on C1 and C2, analytic on C1 and C2 and the annular region capital R bounded by two concentric circle C1 and C2 of radii R1 and R2 such that R2 is less than R1 and both circles are centered at A, then f of z is equals to a0 plus a1 z minus a plus a2 z minus a to the whole square plus dot 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 plus b1 upon z minus a plus b2 upon z minus a whole square plus dot dot dot, where a1 is equals to 1 upon 2 pi I antiderivative over c1 f of w upon w minus a to the power n plus 1 dw and bn, an is equals to this and bn is equals to 1 upon 2 pi I antiderivative over c2 f of w upon w minus a to the power minus n plus 1 times dw. So this is a statement of Laurent's theorem. This Laurent's theorem is an expansion of function which is analytic on the region capital R. Now this is our bigger circle and this is our smaller circle. Both of them are centered at A. Smaller circle defined by C2 and bigger circle defined by C1. Radius of a smaller circle is R2 and radius of bigger circle is equals to R1. W is the point over here and this region is capital R. Now to solve this particular question, this particular theorem, we just proceed as follow. We just make a cross cut between these two circular contours from a point A to B. By making this cross cut, we just make this our multiple connected region to simple connected region. And after making this simple connected region, now by Cauchy integral theorem and formula, we can very easily say that f of z is equals to 1 upon 2 pi I antiderivative f of w dw upon w minus z over c1 plus 1 upon 2 pi I from the point A to B, f of w dw upon w minus z plus c2 f of w dw upon w minus z 1 upon 2 pi I and 1 upon 2 pi I antiderivative b to a f of w dw upon w minus z. By Cauchy integral formula, we can very easily say that a particle if move on this particular curve C1, it would move around anti-clockwise direction, then A to point B, then on the closed contour C2 in clockwise direction, then a point B to A, and finally it would move like this. So this particular region, which is bounded by two concentric circle and cross cut A to B, we can very easily say that value of antiderivative f of w minus z A to B and f of w minus z B to A would be of same numerical value but with of opposite sign. So these two value can cancel out each other, as well as we can also see that C1 is anti-clockwise direction, so it is a positive movement, and C2 is clockwise direction, it would be considered as negative. Therefore f of z is equals to 1 upon 2 pi I antiderivative f of w dw upon w minus z over C1 minus 1 upon 2 pi I C2 f of w upon w minus z times dw. Now out of these two integrals, the first integral is around C1 and second integral is around C2. Now this C1, if we consider this C1, then this case f of w upon w minus z can be expand exactly same as of in the form of Taylor series. If we take this C1 as a circle closed contour C, which is C1, we apply Taylor's theorem for this and we would get 1 upon 2 pi I f of w upon w minus z dw. This is equals to 1 upon 2 pi I antiderivative f of w minus z w minus a dw plus z minus a upon 2 pi I integral f of w upon w minus a whole square dw plus dot 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 dot. Why? Because here z minus a upon w minus a modulus is less than 1. For if we consider C1, then w is this particular point, a is the center of the circle, w minus a, z is the point lie inside this, z minus a upon w minus a is less than 1, or we can also say that z minus a is less than w minus a. So we had applied Taylor's theorem. So this expansion can be equals to a0 plus a1z plus a2z square plus dot 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 z minus a whole square plus a3 z minus a whole cube plus dot dot dot, where a1, a2, a3 are generalization of this integral and an can be written as 1 upon 2 pi I over C1 f of w upon w minus a to the power n plus 1 times dw. So this is the expansion of first part, this one. Now we take second integral. This second integral integrated over around this particular smaller circle C2. For this smaller circle C2, if we take second integral w minus a is less than z minus a. This would gives you w minus a upon z minus a is less than 1. In this case, it is different from Taylor's part. 1 upon w minus z is equals to 1 upon w minus a plus a minus z, and this is equals to 1 upon z minus a, take it common. If we take this as a common, then it should be a negative sign over there, and terms would be 1 minus w minus a upon z minus a, and this is equals to minus 1 upon z minus a, 1 minus w minus a upon z minus a to the power minus 1. Make a binomial expansion of this expansion. We would get minus 1 upon z minus a with in bracket 1 plus w minus a upon z minus a plus w minus a upon z minus a whole square plus dot 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 dot. Now this is one value of 1 upon w minus z. Now multiply this series with minus f of w upon 2 pi I and integrate it over C2. We will get, when we multiply this equation with f of w with negative sign upon 2 pi I, we would get as follows. Minus 1 upon 2 pi I f of w upon w minus z is equals to minus 1 upon 2 pi I f of w upon z minus a plus 1 upon 2 pi I w minus a upon z minus a to the whole square f of w plus and dot dot dot. Now we can take this z minus a square etc. outside of the respective term. We will get this as 1 upon z minus a outside, 1 upon 2 pi I f of w plus w minus plus 1 upon 2 pi I bracket close. Next is 1 upon z minus a whole square within bracket 1 upon 2 pi I f of w upon w minus a to the power minus 1 plus next term would be 1 upon z minus a whole cube 1 upon 2 pi I f of w upon w minus a to the power minus 2 plus n dot 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 dot. Now integrate this particular equation. We would get minus 1 upon 2 pi I integral over C2 f of w upon w minus z d w is equals to 1 upon z minus a 1 upon 2 pi I integral C2 fw dw plus 1 upon z minus a whole square 1 upon 2 pi I integral C2 w minus a with numerator fw dw plus and so on. So this can be written as in the form b1 upon z minus a plus b2 upon z minus a whole square plus b3 upon z minus a whole cube plus dot 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 dot. Here bn is equals to 1 upon 2 pi I integral C2 f of w dw upon w minus a to the power minus n plus 1. Now this is the value of second term of our previous equation. Fz was equals to 1 upon 2 pi I fw upon w minus z dw over C1, and this is fw upon w minus z dw over C2. For C1, we just consider the whole circle, can apply Taylor's theorem, and we would get the result as simple as this much. And for this C2, we just obtained value is equals to this much. Now adding both these parts, we would get Fz is equals to A0 plus A1 Z minus A plus A2 Z minus A whole square plus dot 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 plus B1 upon Z minus A plus B2 upon Z minus A whole square plus dot 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 dot, where A1 is equals to 1 upon 2 pi I an is equals to 1 upon 2 pi I integral over C1 f of w upon w minus a to the power n plus 1 dw, and bn is equals to 1 upon 2 pi I integral over C2 f of w upon w minus a to the power minus n plus 1 times dw. So this is the proof and expansion of Laurent's theorem. So Laurent's theorem is in expansion of Laurent's theorem. Laurent's theorem is applicable when function is not analytic between on a region. In this case, when we expand expansion of a function, we would get positive power terms of z as well as negative power terms of z. Positive power terms of z expansion is same as of Taylor's theorem, and negative power terms of z is due to C2 portion. C2, that is inner circle portion. Okay, thank you.